Great.
Oh, great. Thank you so much.
All right, everybody. Welcome to a Women Who Code backend study group presentation. To get started, we're just going to go through a few logistical details. One thing to take note of, today's presentation is going to be recorded. So if you would like to not be included on the recording, feel free to turn off your video. You can mute yourself. If you feel comfortable, leave your video on. It's a little bit more engaging that way. We might take some screenshots for social media purposes. And at the end of the presentation, we're going to have a Q&A. So if you have questions, feel free to put them in the chat. I'll be fielding questions here in the chat. Or you can save them for the end, and we're going to do the question and answer. So a few best practices, and it's here on the slide that you can see. So while we're doing the presentation, while Prachi's talking, if you don't mind, no multitasking. Distractions just make it hard to concentrate. If you're not talking, which should basically be most of the time, unless you're Prachi, then keep yourself muted. We would like the presentation to be interactive. So if you need, there's a raise hand button. But again, for the most part, save questions for the end. Otherwise, we'll be answering some questions in real time in the chat. Now, by attending this event, you agree to comply with the code of conduct of Women Who Code, and that code of conduct can be found at the website womenwhocode.com/code of conduct. All right, moving on. So, welcome to the Women Who Code presentation. The mission of Women Who Code is to empower women to excel in technological careers. This is the backend study group, which was created by your host, Prachi Shah. And the goal of this group is to learn and discuss backend engineering concepts. So today is part 2 of a 3-part series. For those of you who were here last time, in part 1, we covered the front end, we covered some back end, and we talked a little bit about what is system design. Today is part 2 of the 3-part series, and today we're going to talk more about system design. Prachi is going to tell you about design considerations. We're going to talk about how to scale systems. We're going to talk about how to manage data, and at the end of all this, again, we're going to do a question and answer. And also, if you like this presentation, there's going to be a feedback form. I'm going to give you a link to the feedback form at the end. And if you want to fill it out, that would be super. Next week, by the way, is going to be part 3 of this presentation. And so that next week, March 6th, Prachi is going to cover interview questions. So now I'm going to hand it over to Prachi Shah, your Women Who Codes coder, and she's going to give you this awesome presentation. So here's Prachi.
16th. Olga, that's March 16th. And Matt, thank you for hosting our session today. He is a friend, he's a volunteer at Women Who Code, and he's a very successful startup founder. A little bit about me. I'm a senior software engineer at Unity here in San Francisco and a director at Women Who Code San Francisco. And I founded the backend study group, and I've been leading this study group since 2 years now. For those who are new here, welcome. We are happy to have you here. And for those who have been with us for a while, thank you very much, and happy to see you as well. Yeah, so get started. In every session, I usually cover a little bit about what backend is, just for context. So backend engineering is where we design right? Architect, build, and maintain server-side web applications, stuff that is on the stuff that the user or the clients don't usually see. So it's everything behind the scenes where there's business logic, application logic, databases, servers, and a whole lot. Some of the concepts that become important when understanding or learning backend engineering would be client-server architecture, networking, APIs. We need to also know web fundamentals, because a lot of time we are building applications for a client on the web. Microservices, databases, security, operating systems, distributed systems, there's a lot. And some of the technology stacks that are part of backend engineering would be Java, PHP, .NET, C#, Ruby, Python, REST APIs, AWS, and so forth. So system design, right? So like, why do we do system design? Right? Well, like, what is system design? Basically, you're designing a system, an application stack, right? A product to either like solve an existing problem, right? Or build a new product or a new feature or a new platform, right? From scratch. So there are two reasons why we would want to design: solve a problem or build a product. When we are designing, what are we actually doing, right? Like, we are defining the architecture at the high level. At the detail level, we are defining all the modules. We are defining what the interfaces look like. And we also want to understand what the data looks like and what is the data flow. Architecture here means, like, defining the behavior and the high level view of a system. Like, what are we building? What does the behavior look like? Is there a user? What does the user behavior look like? If there's a data, what does the data manipulation of behavior look like, right? So the high level, we want to understand what are we doing here. Modules are a little bit detailed, where, our system can have smaller different modules, each have their own functionality, one core functionality or a list of functionalities, and each of these modules interact with each other to accomplish a task, right? Interfaces is the communication. Basically, how are these modules communicating? There can be 10 modules in an architecture in a system, and all of them can communicate in different ways. And that is what we want to define, right? What is the communication? What are the interfaces? And data flow, right? Pretty much every application, every system now deals with data. So we want to define what the data looks like. We want to define the flow of data in the system, what is information, what is data, how is it transforming, how is it changing, how are we persisting, right? All of that is what we want to think about, and all of this is part of the system design. And if I just summarize, we basically, what we do is we define an input to a system, we define an output to the system, we understand the business rules. If there's domain knowledge, then there comes the business rules, and then the data schema and flow of data. These are the design considerations, when we are thinking about system design. These are the things we need to consider. Consider this as a template. Every time you're doing system design, these are the things you have to keep in mind. Requirements of your system may vary. So there can be a situation where you don't need to necessarily decide if you want to use SQL data or no SQL data. I mean, your data is like banking data or finance data, then it's kind of clear that you would want to go with SQL, right? Or relational data. So you would not want to necessarily have this debate of should I pick SQL or no SQL, stuff like that. So requirements can vary, and the magnitude of what these considerations are can also vary. Maybe some system doesn't have to be available 24/7, right? It can have a downtime, and that's fine. The system you're designing doesn't deal with a lot of incoming traffic, so we don't need a very sophisticated load balancing algorithm, right? So, okay, fine, no problem. So, but this is a complete template of all the things we need to consider when we are doing system design. So we start with scaling first, right? What basically scaling means is, as your application grows, you're adding more features, you're adding more requirements, you're collecting and processing more data, you're interacting with more users, your performance of your application needs to change. It needs to be consistent consistent as expected, or needs to improve, because now you're dealing with changing dynamic application demands. That it can be from the infrastructure side, it can be for the users, it can be like now you're dealing with a lot more data. So scaling basically addresses how do you deal with growing application demands, right? Application needs, while not compromising your performance and efficiency and even costs. Availability is, you have a system, it has to be it has to be up and running, right? You want to minimize your downtimes or don't even have a downtime. And you want to always have a system that's up and running. Like if you're buying something on Amazon, even if there's an underlying payment system and it's down, a user won't be able to complete their order because the payment didn't go through. The credit card was not processed or the debit card was not processed and payment system is down. So a user cannot complete the order, and that causes Amazon to have a downtime because underlying system is down, right? Stuff like that. So you have an Amazon.com shopping site running, you want to make sure the underlying payment system also has a good uptime and it's running. If I'm ordering something at 1 a.m. at night, let's say I need to make sure that even at 1 a.m. Amazon is up and the payment system is up and running. And if you have a downtime, for example, for like maintenance needs, make sure that that's scheduled and accommodated for. Reliability is system performs the task as expected. If Amazon.com is supposed to help you search for items and make an order, it has to work like that, right? It has to perform as per the expectations. It's a site or a product. It has 5 features. The features have to work. So the system is reliable when it's working as expected all the time. Robustness is when functional when errors or disturbances, right? Even if there is errors or disturbances or exceptions, your system is robust enough to deal with them. You either planned for these errors and you already know how to address them if these kind of things happen, or if some errors or disturbances happen which are out of your control, your system can very well deal with them and still be functional. And that is what basically robustness is. Load balancing, right? During peak hours, if your network traffic or incoming requests increase, your system needs to be able to deal with this incoming traffic and deal with this load, right? It has to balance this load or this incoming traffic, which will be distributed across servers. So load balancing is where it helps us manage network traffic. Caching is like an additional data storage layer. What we're doing here is we'll talk about caching later in a few minutes, but what we're trying to do is we're creating an additional layer for data storage. And there are reasons why we would and would not want to cache, and we'll get into that shortly. Data partitioning. You want to distribute your data across systems to improve query performance. There are benefits to this. You don't have a single point of failure. Data is distributed. You can do a lot more in your application code when you have a distributed data. There are benefits to that, but it also adds complexity in your system. And we'll talk about this as well. SQL versus NoSQL. You're designing a new system. You would want to consider, right, what your data storage looks like. Is it relational, where your data is related and there is some structure to it, or NoSQL, where your data is not necessarily related and it can also be completely unstructured data. So this is something to consider, and we'll talk about this as well. Performance, you want to be glitch-free and fast, but performance always comes with a set of compromises. So you need to come up with like, what is my performance needs, right, of my application? And you have to determine that, and you have to come up with that, like how fast do you want your APIs to be or your site to be, or how fast you want your page to load, right? So maybe make light pages and not like heavy web page with lots of stuff going on and lots of integrations, right? So you have to come up with what is a glitch in your system or your application, and how can you accommodate that, and also how fast you want your application to be. Extensibility is future growth. You want to design a system that can be extended. You want to keep extensibility in mind. Today I'm designing for 10 users, but tomorrow, maybe as my product grows, maybe in a year, I will deal with 100 users. Now, what does that mean? I only designed my application or my system for 10 users. Now I have 50 users and my system's crashing. So you want to design your application for extensibility and assuming or considering there will be some future growth. And then error handling and security, where, error handling can be as simple as validations on your UI, or, if there's some faulty behavior, then you can provide a very smooth user experience. And security is, how are you collecting your data? What kind of data you're collecting? Is it PII or not? How are you securely persisting the data and transforming the data or handling the data as it flows or moves through your system? Next slide. Yeah. So a few things. This presentation is like, I'm going to talk about all the things that we need to know when it comes to system design. There is no like, you need to know this first and that next. These slides are things you need to know, and that will really help you not only understand a new system or new code base that they are trying to look at, but it also help you have like a system design thinking. This is surface foundational when you are doing system architecture. So monoliths, right? Like, what is a monolithic architecture? Basically, your entire application stack resides on one server. So it can be your business logic, right? Your code, your APIs, in this example would be RESTful APIs, your UI, so it's like your HTML pages, CSS, JavaScript images, all files, and your database. They're all bundled and they're all deployed or running from one server. So all your code and database is single server system. The problem here is if you want to scale up, you can only like add more CPU or like memory or external disk space to this server. So you can only scale vertically because you have one server, you can only scale vertically to just add more resources. What this causes is after one point, you'll run out of resources you can scale up to. So you can only scale to, let's say, from 1 user to 50,000 users. If you want like 5 million users, you just cannot. The system will not support it. So you want to use a monolithic architecture when an application is small and simple. It's not going to grow much in the next 5 years, not with users, not with like how complex your application is, what features you're going to add. Right? If you created something very simple, then monolithic architecture is the way to go. You do not want to overcomplicate your architecture. The only negative, the other con of this is such a system is a single point of failure. If your server goes down for whatever reason, your application is down, like nobody can access your system or your application. So like this can be very problematic, and sometimes it can be network failure. It can be as simple as your server is in a room and electricity goes and then your system is down. Like it can be as trivial as that, but it just like your system is like completely down. So it's a single point of failure for any kind of failure, right? Longer downtimes, basically in such a case, if single point of failure happens and an error or exception happens that you are not equipped to deal with, then, you will need to figure this out all on your own. Make sure that one server is up and running. There can be all sorts of problems that happen on the server that you don't even know how to debug or fix. So it can cause longer downtimes and you don't have a replica of the system, nothing. So it's very risky like that. So you want to like make sure that, the code base in there or the application you're having is not super critical or it doesn't have to be up and running all the time. If it's downtime, if there's a longer downtime, it's fine. Like you're not losing money, no clients are getting mad, stuff like that, right? It's something simple that is down. There's a downtime for like an hour or so, fine, we will deal with it. That's fine. So to the right, if you see the diagram is like, the middle, sorry, square is like your business logic, your APIs, your UI images, all of that is like same on the same application, and your database, all of that is all stacked on the same server, one instance. The diagram to the bottom is that of an e-commerce application, there are different clients. So there are two different kinds of clients. One is on the web, so your desktop browsers, right? All 5 browsers would be, let's say, 5 clients. And then your one mobile device. You have 6 clients. Your load balancer is balancing the load. But like, if you see all of that, your order service, your payment service, your catalog service, any other storage, all of that is this one system. It's a complete monolith. And, if for whatever reason order service goes down, your entire application is just like on halt. Like you cannot order at all using this e-commerce application at the moment. So you have some kind of error or downtime till that is resolved. So you need to be like an expert also at like a lot of different things to manage this whole one monolithic architecture. And that's like the biggest downside of choosing such an architecture. It's very simple, but if single point of failure and can be very complicated. The alternative to that is a microservice architecture. Now, what you do is you distribute or divide your application code and your resources into different servers. So your entire application stack resides on more than one server, right? So your business logic can be one server, your APIs can be somewhere else, your UI can be a different server altogether, and your database is hosted on a totally different server. And all of these different servers interact or communicate with each other in a cumulative manner. Cumulatively, it's like your entire application, right? But behind the scenes, it's one application. Behind the scenes, like 4 servers are supporting it. And scaling is really easy with this kind of application, because you can just add more servers and more databases. So you can do horizontal scaling. You can, of course, do vertical scaling, right? Where one server, you can add more resources, but you can also add more servers. You can have like 2 servers that serve your business logic, or 3 servers that serve a UI, right? So stuff like that, you can totally do that. You can architect that, you can make such decisions. Higher availability, again, because no single point of failure. If there are 2 servers supporting or posting my business logic, if one goes down, there's another one. There is availability, so no problem. Almost minimal to no downtime, right? Like lower application downtime, and maintainability, right? Like it's very easy. Like you have your code, you just replicate on different systems. You can easily maintain the entire system, and you can scale it up and down as you like. Again, this e-commerce application, right? If you see, there are different clients on web and mobile. There's an API gateway, and this API gateway is taking care of distributing the traffic to which server or which microservice does the traffic or incoming request need to go to. If if a user wants to access a shopping cart, then we don't necessarily need to show them ordering information, right? They're still in the cart, so the request can go to the server that's holding the shopping cart microservice, and it might have its own database, right? And all of these are interacting with a single message broker for streaming. So stuff like that. So like it's more distributed. You have more resources that you can scale up and down with. And to the diagram is like, now everything is split into different servers and different microservices, and each of these microservices can have their own databases that store very specific data. And then the application code is responsible for fetching all different kinds of data, getting them together, and presenting a clean and clear or complete view of the data to the user, right, in the UI. Scaling, right? So now we need to talk about scaling. Like, as your application grows and as your application demands may grow, right? Like you need to add more features, or your users are growing. You need to deal with that. They want more features. They are coming up with a lot of bugs on your site. You need to fix them. There can be all sorts of needs. You're collecting more and more data now because you want to, improve your features or provide more functionality. And now all these things are growth or demand needs, right? Now, eventually your application, your product, your system, your platform, whatever it is going to reach a point where this is something that's unavoidable. You have to address this. You already either plan for it in your initial design, or you address it when the time comes, right? Now you have to deal with it. So we need to basically, sorry. So when it comes to scaling, there are 4 things we need to keep in mind. We need to understand if there's an incoming traffic from the users, right? How do we efficiently load balance in a way that there's reliability, there's availability, there is good performance, there are fewer to no errors, and the system is reliable. It's functioning as expected, right? So what is load balancing, right? And how do we enable it or address it? So that's something that's very important that now we need to think about as we scale our application. Caching, right? As we're dealing with more and more data, depending on our data needs, depending on our read-write needs, we would want to consider caching. And if we do, then we will need to understand what strategy it would be and what caching tool or framework we want to use. So caching becomes very important. And the other is data partitioning or sharding. This is more on the core backend side or database side or data store side, where we need to think about like one single database is not enough for me to store my all of my data, right? I might want to consider a relational database. I would want to consider like a data lake or a data warehouse, or I would want to consider like a NoSQL database. I need to figure that out. And that's where data partitioning comes. And that's also where we need to think about what kind of data we want, SQL or NoSQL. And then depending on our application needs, we also need to kind of understand, if it's SQL data, we need to understand what asset properties are. And when it comes to like basically non-relational data or even big data, we need to understand the cap theorem, because that is what we will be providing. Our system will be providing. So we'll look into that. When it comes to like very high level scaling concepts, there are two ways you can scale a system. First is like vertical scaling, where you just have like one server stack and you're just like adding more resources, right? Like let's say a lot of people shop at Amazon between 5 p.m. to 7 p.m. after work, but like barely anyone shops at Amazon from like 1 a.m. to like 6 a.m. Let's say US time, right? Or PST, let's say. So in this example, we want to like scale up our application, right? Our resources between 5 to 7 p.m. because that's peak hours. We are getting much more users there. But after midnight, after 1 a.m., we want to reduce our resources, right? Because why waste resources and why spend that money when using the application, right? So you want to scale down. And that will help you save costs. So vertical scaling is basically adding more resources like CPU, memory, external disk drive, and stuff like that to your existing system. You're scaling up the resources on that server or system. Horizontal scaling is you're adding more devices or more servers or more databases to your application. And what happens with horizontal scaling is that now you have a distributed system. So the application code can be in 5 different servers. Your database can be on 3 different servers. Your cache can be on 2 different servers. And you have this entire system which is distributed and which is communicating. It can be distributed within a geographic region too. Like some of my servers are on the East Coast, some are on the West Coast. Fine, they do communicate for my entire system to run properly, right? In a reliable manner. So stuff like that. And you can also do hybrid, which is, you know, like depending on the peak hours or your application needs or performance needs. Sometimes you do vertical scaling, sometimes you do horizontal, sometimes you do both. So depending on your use case and what performance and efficiency you want to provide, you might want to consider doing both for your application. Yeah, so load balancing, right? So what is load balancing, right? Like load here basically is incoming traffic, incoming client requests. That is your load, and you need to distribute it, balance it through your system. So, you know, one system doesn't get all the incoming traffic and it just like it's out of all the resources and it's completely exhausted and it might shut down because it doesn't have more resources to deal with incoming traffic, right? So you want to balance out the incoming load or the incoming client request amongst your distributed resources. So, you know, your system does not overload and it functions properly. Right. And here distributed resources can be in any number of application servers, web servers, databases, cache, anything, right? Or any resources you have within your system. So you want to properly balance that out, incoming requests. This, like I said, prevents overloading your resources, right? So they don't run out of memory or they don't shut down because, you know, it's like functioning at a very high capacity, which it may or may not be designed to function at, maybe even for longer periods. So you need to like understand your system limitations, your device limitations, and make sure that those limitations are not met often, and you need to distribute them. Otherwise, your system can become dysfunctional. What this also helps is with like no single point of failure, right? Like let's say I have 3 application servers that are making sure that Amazon.com, which is my application, it's running up and running fine, right? If one of my application servers is down, my load balancer will only route traffic to like the other 2 application servers and everything is working fine. So like the one that was a point of failure, the application that failed the application server that failed will not receive an incoming request till it's fixed and up and running, right? Then again, you distribute among all the 3 servers. So stuff like that. So that way you don't have a single point of failure, right? Because you have a distributed system, and load balancing makes sure that all your resources are optimally used, right? Distribution can happen across your hardware or software, right? So it can be like, okay, let's add 3 more physical servers, right? This gives you higher performance, but it's hard to configure hardware and it can be expensive. The other is software, right? Like you can have some kind of algorithms and some kind of, you can have like a server or a virtual machine that acts as a new instance or a new system, right? It's easy to configure, and it's also inexpensive. So software is preferred. An example would be Nginx Plus. It's like a very famous like load balancer, which takes care of incoming traffic, security, and a bunch of different things. In this example, if you see, right, like we have all these clients and users, they are trying to hit this load balancer that sits between the internet, the client, and the backend, right? The front end and the backend. And the software load balancers take care of load balancing traffic with let's say different virtual machines, and hardware load balancers to take care of like distributing traffic among actual physical devices, right? So and all these load balancers have like sophisticated algorithms on how they do load balancing. So we will, it's important for us to kind of like understand what these algorithms or these traffic routing algorithms are. So there are a lot. I just like focus on like the most known or the ones that are easy to understand. So, round robin, basically like you have like, let's say in this example, in the diagram, if you see, right, like you have like the diagram to the left, you have like 6 servers, right? Like you're just distributing 6 machines from where the incoming traffic is coming. You're just distributing in a round robin fashion. So if you have server 1 and 2, request from laptop 1 is going to server 1, request from computer 2 will go to server 2. Then again, 3 will server 1 and 4 to server 2, right? So it's a round robin fashion. So it's back and forth. If you have 5 servers, it will just go in like server 1, server 2, server 3, just in round robin fashion. So what this will do is like all machines eventually get to like, deal with the same number of requests, right, per server. So server 1 gets to deal with like 3, server 2 gets to deal with 3 as well. So it's like similar, the amount of load they need to deal with, like the traffic that these servers need to process is similar. Random is like a load balancer is like a random number generator to select a server. Like let's say there are like 10 servers. There might be like some random number generator function, which will say, let's pick 5. And that's for the next incoming request, server number 5 is what is going to process that request. So it can be very random like that. Least loaded is, this is a smarter load balancer where, let's say you have 10 servers and server number 8 and 9 are handling much less requests than the other servers at the moment are. So you want to redirect this new traffic to the server that is dealing with the lowest number of active connections, right? Because then the other servers are not loaded and these servers might be even idle. You want to move our router traffic to those servers. Application specific. So, your application can be something very vast and you have 3 servers dealing with like, let's say there's like a banking institution, financial data. You have 3 application servers dealing with like payments. 3 are dealing with like transactions, and the other 3 in the system are dealing with like, some like user management or some kind of profile management. If the incoming request is related to payment, then route it to one of the 3 servers that deal with payment needs, right? Don't route it to the one server that's dealing with like user profile, or user account, right? So it can be application specific. And this is again a very smart load balancer and has information about the underlying applications. You can configure that. In the diagram to the left is the classic round robin, and to the right is like, your least loaded. The server that's least loaded will have the new requests coming in. Caching. Caching is, as your data grows, your application grows, it's something that just you have to do. It like solves a lot of problems, and it makes things like data management fairly like easy for very complicated, ever-growing applications. What you're doing when you're caching is basically you're optimizing your system, well, ideally, for read operations. Querying the database, your data warehouse, your data lake, whatever it is. These are very expensive operations, not only in time, but also in cost, right? So what you want to do is you want to have a simpler, easier, cheaper cache that ideally sits between your client and your core data storage, which from where you can read data and serve to your clients, right? This reduces cost, makes your application like basically providing data faster, and it's less complicated. So you want to implement the cache to ideally improve your read operations, make them faster and simpler and lighter, right? And also save costs in this process, which is like a very big consideration when you're doing system architecture. Like cost is number one, if not, cost is actually top 3 considerations, really. What this does is like, because you're hitting a cache which is closer to your client than your actually core storage, right? You are reducing load on the servers and databases, right? Cache will handle a lot of requests, and it's faster, it's lighter. So you're protecting your backend like database and servers from like a lot of incoming requests, cache access, some kind of protection there. And you're optimizing for distributed traffic management, right? Like your cache you can have all different kinds of caches implemented across geography or like depending on an application too. And this will just help with like a much better or distributed traffic management. Traffic management here is again, ideally read operations. You want to read, there's some requests coming from the client where you need to read the data and show them, present them, right? On some dashboard or something, right? There are a few different ways in which you can do caching. One is like the client side and with CDNs, right? So you can be caching your entire page, web page data in your browser. It can be also like, like in a CDN, like a content delivery network, which can cache like images or media, right? So that would be on the website or the front end side or the client side is where you are caching data. So you don't need to like query the application, the database every time you want to load an image or reload the entire page, right? Like your browser is storing a copy of it, or your CDN is storing images and audio or media. So they will just present it. So like the round trip time is like very minimal. You're not even hitting the core storage or the application in some cases. Web servers, there are like two different ways. You can do caching here. One is reverse proxy, where like server to redirect like request to web and application servers. Reverse proxy basically is for redirecting incoming requests to your underlying web or application servers, but proxy can also cache, just like, it can cache like a web page, it can cache like images and some other configuration and application information. So that will definitely help with on like the server side or web server side. And like I said, it can cache requests, it can cache like static content, media, all sorts of things. Databases, like you can have like a cache layer implemented for a database. And this is ideally, you start doing this for like read heavy requests, right? Like your application can be very read heavy and like not too write heavy. Then you want a cache system that just like read data from and just present it, right? An application. So at the application level, you might want to have some integration with like Memcached or Redis, which are like key value store. Redis is key value store. It's a cache layer that can sit between your client and your application or data storage and can do caching for you. Here, you are just storing data, which is of type key value store, right? With Redis. So if that's something, that is how your data is structured and that's all you need to present, then just have some kind of key value data structure or store, which is Redis, which will help you with serving your incoming like read requests much faster. Querying the database or your data warehouse is always expensive. It's time consuming. It's costly. So caching will definitely give you those benefits that it's faster, it's less time consuming, right? And it's cheaper comparatively. Caching strategies. So there are like a few different caching strategies. There are many actually. I again, in the interest of time, I've just mentioned like the most known caching strategies. So like cache aside, right? Like what you want to do is you want to read data from the database on cache miss, update the cache, and then basically what happens is that what you want to do is you want to, for any incoming read request, you want to read the data from the cache first. It can be like a Redis instance. If you don't find that data in the cache, then the client will go and read the data from the database and show that on the front end. But as it's reading data from the database, it's also writing that data to the cache. So next time, if it wants to read the same data, and if it will go again, try to read from the cache, it will find it. So now you don't need to go and read the same data from database again. So if the cache miss happens, read from the database, but also update the cache at the same time, right? If for a repeated request. This is time consuming because of if a cache miss happens, now you have to like, you're reading from the cache first, miss, right? So that's one. Then you're reading from the database, that's two. And then you're updating the cache. Like 3 operations happen. So it is time consuming. And you have to set like a time to live, right? Like you need to make sure that if your data is very volatile and ever changing, then you would want to set like a time to live. This is when TTL is when data on your cache is invalidated. So you can be like, okay, I need to store weather information for the next 1 hour only, right, in my cache, because after an hour, maybe the weather information for the day changes. So I cannot keep the weather information for today in my cache for like 10 days. It has to expire in an hour, because in an hour, I have more information about how the rest of the day, how the weather for the rest of the day is going to be. So at that time, like your cache will have invalid data after an hour. So you'll have to read from the database, put it on the cache and stuff like that, and set a TTL, which will be very short, like an hour. Some applications have TTL as short as like 30 seconds, 5 minutes, like 15 minutes. It's very common. Write through is another strategy where, cache is basically the primary data store. So your cache is where you store all your data, and any data that you collect from the user, you always store in the cache. And then the cache will update your underlying database. So your underlying database acts as a backup as such. Your database might not be the most up-to-date, because your cache needs to make sure it's updating your underlying database correctly and on time. So cache has the most up-to-date data, your database doesn't. And if for whatever reason the cache instance like fails, or some error happens, there will be inconsistency between your cache and your database, because your database never got updated. The cache is most up-to-date, but database becomes unreliable. So now you have to make sure that they are both in sync, right? So that's an additional headache, but that's right through. Right behind or right back is application. An application has control over updating the cache, and it will also synchronously update the database. And if there are any system failures on the application side, it can cause the cache and the database to be inconsistent, and your data is like completely inconsistent, and now you have to deal with that. So like application has control over what to do, but the application has to be very robust and has to deal with system failures to make sure that the cache and database are up to date. Because if it's a read heavy application, then your users might want to see the most latest updated information, and your cache and database, depending on how application uses these two data stores, like they need to be most accurate and up-to-date and available, the cache and the database. You can also do this distributed caching. It doesn't just have to be adding a cache layer. Doesn't have to be one instance, one application, one computer, right? One server, one system. It can be distributed, across your data can be distributed across different caches. It can be different kinds too. Like some of my data is on Redis cache. The rest of my application data is on mem cache, and that's fine. That's my application needs. I have different kinds of caches. I can have different kind of CDNs where my data is there. It's distributed. It can be distributed based on like the geography too. And my data store or databases can be different, right? Like I can have a NoSQL data and a SQL data and something else, and or data lake or data warehouse, and that's fine. My entire application stack collects a lot of data, but it's all different kinds of data at different point, and they're all distributed and persisted in all different ways. And it's complicated, but some applications have such needs, so you can totally do that. Cache invalidation happens when the data you persisted on your cache needs to be rewritten. It's expired, and you need to be invalidated. It's not valid anymore. It's not accurate anymore. It's not up to date anymore. And therefore, that is not the data you want to deal with. Your application or your user need to be dealing with. So there are a few ways in which you can configure this. You can invalidate the cache that you have built is first in, first out, right? The data that was the old days, basically the data that you put first in your application needs to go out first. So let's say your cache has 1 GB of data storage. The data that was inserted based on time, first you remove it first, right? Last in is the data that you inserted the most recent or last, you remove that based on time. And this is purely based on the time and the storage. It doesn't deal with what kind of data it is. There's no need to understand that. It's just time based. LRU is least recently used. You might store all sorts of data on your cache, but some piece of data is not frequently read from, whereas rest of the other kind of data is. So the one that's not like, it's least recently used, you want to like, it was like used, like your cache is, you store data in your cache for 10 days and this some kind of data is not used since 10 days, right? So just delete that because it's like least recently used. And least frequently used is like fewer reads, the kind of data where you have like very few reads, then you want to swap that out to add more data or different kind of data or just update the data, right? So again, there are more invalidation strategies, but these are some of the like very common ones that are used. This brings us to like data partitioning. Data partitioning is a very important concept. Like as your application grows, you deal with all different kinds of data. You might deal with big data too. You need to split your data across multiple data stores, even multiple tables. And this is what partitioning is. Your data is split across different systems, different tables, and you need to come up with like, what does that partitioning looks like and how is your application going to deal with this data? Ideally, well, the benefits of this kind of or data partitioning are you want to improve maintainability of your data, right? You want to improve performance. You want to improve your application and data availability. This will also help with load balancing your data needs for your application and cost effectiveness as well, because like certain kinds of data is like more read heavy or more frequently change. You might want to like partition that in a specific way for read heavy needs, and that might be more, you want to make that more cost effective and stuff like that. So like data partition becomes very important when your application is scaling, growing, and dealing with lots of data and functionality. There are two ways you can partition your data. The first one is like horizontal partitioning, which is called sharding. Basically, you're dividing your data into partitions, or it can be different data stores, or it can even be smaller tables, a few different tables, right? And they are all accessed separately, right? Like it's like separate tables, separate partitions, separate systems. They can be accessed separately. They don't have to be all accessed at the same time to make sense. What you need to do is you need to, you need to come with an algorithm on how you partition your data, right? Like, let's say you have some data about a person and their location, their name, and their address, right? Like now you have an application that stores all this information about people's name, address, and phone number. How are you going to deal? Like, it can be about like 7 billion people. How are you going to partition this data, right? So there is some kind of routing algorithm which can decide you need to partition all this data into like 10 systems, 10 partitions or 10 shards. And this kind of data will go in shard 1, partition 1. This kind of data will go in partition 2 and stuff like that, right? So a routing algorithm will definitely like help you with this. A very easy way in which, you can do horizontal partitioning or sharding is data range based. If you understand your data very well, you can divide, partition, shard your data based on a range, right? Like, for example, zip codes, right? Like all zip codes that start with 9 and 5 should be on partition 1. All zip codes that start with 8 and 5 should be on partition 3. Stuff like that, right? Or location, information about everyone who lives in the West Coast should be in the West Coast partition, right? Information on everyone who lives in the East Coast should be in a partition where we store information about East Coast residents, right? So if you know your data enough, very well, and if it's structured or clean enough, IDs, I have like 100 people in my system, people with ID 1 to 20, right, can just be like in partition 1, and then 21 to 40 can be in like partition 2, stuff like that. So this is very common and it's easier way of partitioning. But if your data is super complicated, there are all sorts of like routing algorithms that you can use for partitioning. When you do horizontal partitioning, all your partitions have the same data schema. So all your data structure like looks the same. If there are 10 partitions storing zip code information, then they all have the same table, they have the same data model, the same data schema, and the data looks similar, right? They'll have all these partitions will have the same 10 columns, let's say, for storing some person's information, right? The location, name, address, phone number, let's say. So it's very similar, the schema. You can easily add more machines for better load balancing, and you can shorten response time too for querying. Because if I only want to query people whose zip codes start with 9 and 5, then I only need to query one partition because that's the only partition that stores this kind of information, right? I don't need to query all of the 9 partitions that I have, right? So they shortens response time, querying is faster, load balancing is easier because when there's an incoming request for new data or even reading, you only read from that one partition, only read to write to that one partition. So it makes it very easy for load balancing and definitely efficiency. It's better with scaling your data like that. Uneven distribution, like now you have like your zip code information, right? In like 5 different partitions, let's say. Your application code needs to be smart enough, or you need to add this functionality in an application code to read from 5 different partitions, collate all that data, because it's uneven distribution, right? You collate all that data and then try to make sense out of it and then present it to the user. So depending on an application needs, you might want to, yes, all these partitions store different data, specific data, but if you want to show like, give me all the people residing in zip code starting with 9.5 and 8.5. Now my application code needs to be smart enough to query 2 partitions, get all that data, and then properly like collect it, structure it, and then present it, right? So application needs to be smart enough to understand this request and deal with the querying. Vertical partitioning is, applications feature-wise distribution of data. What this does is like, let's say again, Amazon.com, right? Some of my, it has 3 features, let's say, like showing, if I do a search about books, it has to show all the books. If I am like, like doing payments, it has to show information about payments. If I go to orders, it has to show information about all my orders, right? So this partitioning can be like distributed, right? Like it can be application or feature specific. So there are 3 partitions that store everything related to orders. Internally, these partitions can follow horizontal partitioning algorithm, that's fine. But there are 3 different partitions that are storing information about payments, and the rest are storing information about like, all the books listed on Amazon.com. So these partitions are different. So if someone wants to search for books, only go to the 3 partitions that are specific to this feature, right? This application, like searching for books. And internally, these 3 partitions can have horizontal partitioning, vertical partitioning, further down is all fine. It's all can be configured. But vertical partitioning application or feature specific distribution. So like it's easy to implement because, it's very clear what the partition is going to do feature wise. It is low impact on the application, but your data might be different, which is the challenge here, because books storing information on books can be like, very specific things. It can be a relational database. It actually doesn't even have to be a relational database. It can be a document store or a text or a blob, right, which stores information about books. But payment information is transactional, so it might be relational database, right? So order information can be even document store or even a table. So depending on your shard or partition, the schema can be different because the data looks different, because a different kind of application or feature need that this data is supporting. This is an example of, very simple example of like partitioning, where you have your original data, right, at the top. These are the 4 data points you're collecting. If you're doing vertical shard, to the left, VS1, VS2, then your one shard, first vertical shard may store information only about names of a customer. And your second shard is storing city or location where they live about a customer, right? So if you want to, if your front end is like, okay, or your user needs to know all the information about themselves, you need to the application needs to query VS1 and VS2. But it's a very specific needs. Location data is all in VS2. First name, last name, information data, or contact information can all be in VS1. So application specific, feature specific shards. Whereas horizontal shards, if you see HS1 and HS2, it's like, record starting from 1 and records till 2, they should all be in HS1, and records from 3 and let's say beyond, they will all be stored in HS2. So it's like range based, and your range here is customer ID, and it's just like serial number, right? So that's your range. So stuff like that. So you can decide how you want to partition, and there are like few different algorithms on how you can do that. This brings us to like data schema. Understanding your data, what you're collecting, what you're processing, how you're transforming your data, how you're manipulating your data, what is the data flow. You need to really understand what your data structure looks like. right? Like, and what does it mean? There can be like domain specific information that you're collecting that your data has, which you may or may not understand. You need to like educate yourself on what data is and how valuable it is and what all you can do with it. Like, data is powerful. There are a few different kinds of data. Therefore, like, there's structured data, which is like a best example is the SQL data or your tables, right? Relational data. If you look at the diagram, it's like a table and it has like the objects or entities have some kind of relationship between them. It can be semi-structured, something like, a JSON file or something like an XML, right? So the structure, semi-structured because, it's like there's no relational data, but JSON has a structure, XML has a structure or format to it. Therefore, it's semi-structured because it's not like SQL data, but there's some format or structure to it. And then it can be unstructured, which is just blobs, right? It can be images, it can be audio files. This can be stored as like some kind of binary data. So it's completely unstructured. Some of the common data types or database categories, therefore, are your classic relational data, right? SQL. You have your tables, which is rows and columns, right? Like your tuples and attributes. Best examples are SQL, Oracle, right? MySQL, Postgres. So these are like very commonly used SQL databases. The other kind is like the rest are all considered NoSQL, right? Like they are NoSQL or non-relational, right? So very famous kind of data store or data type is your key value, where your key is some kind of identifier and value is some kind of value to it, right? So in the previous example, if I had to store customer information, right? My key would be customer ID and my value is their first name and last name. So it can be like a multiple value, but it can be like, or as simple as key is customer ID 1, value is first name, Alice, right? That's it. Or all I need to know for my front end is I need to know the customer and their city. So key would be 1, value would be city, Austin, right? So stuff like that. Redis is very famous, like very well known key value data store. It's almost always used as a cache. Column wide would be like flexible columns. It's not your traditional relational column. These columns are flexible, they are distributed, and every column can look different and can have different kinds of data, and it can also be distributed. So it's like very flexible, dynamic columns. And Cassandra is very well known column-wide data store. Graph is basically your relationship between different objects, right? Like Facebook is a good example, right? Underlying data structure is the graph data structure. Two friends are connected. They are different objects, different people, different entities, but they have relation. They are connected. So it's your traditional, typical graph data structure in computer science. That's the idea. And OrientDB is a tool that is like, your graph data store. Document is like query like JSON documents. It can be just, your document can have any structure. It's just your static content or it's just text. Basically, MongoDB is a very well-known like document data store. And a blob is basically binary data. So it can be audio, images, any kind of media. And at the bottom is just like a pictorial description of these kind of different data types or even different databases. We are reaching the end of the session. I'm sorry we are going a little bit overboard, but if you're still here, we just have a few more slides. Since we're talking about like data, I felt like it's important to just quickly revisit SQL and NoSQL, because you need to understand like like I said, right, your data, so you know what partitioning is, what caching is, and stuff like that. So I felt like it's important we revisit some fundamentals here. So your SQL, right, it's your classic relational database management system. Data is stored in a tabular format as rows and columns, right, tuples and attributes, and tables have a relationship between them. And your data model is rigid because, it can grow, but like typically it's rigid. One table is only about customer information, so it's only going to be restricted to that. One table is only about payments. One table is only about storing different kinds of books we have on our website to sell. You will only store information about books. You will not store information about customer, right? Stuff like that. So like your data model is rigid. It can grow as you can add more data points to it, but you would not want to store different kinds of data in one table, right? It's very specific to the entity that we are designing for. Pros would be, again, no extensive coding is needed. Designing a data schema is very simple. You just need to know all the data points and into the relationship between different entities, and easy. Almost everyone is familiar with SQL commands at this point, right? Or SQL DDLs, DMLs. So everyone's familiar. So it's easy. Learning or ramp up time is not a lot. Supports asset properties, which we'll look at in just like shortly. Suppose joins between tables. So, you can establish new relationships as your data grows, right? And it's, again, high in demand, great user community. It's like everyone knows about SQL. So like you have all the support in the world to learn these technologies, implement them. There's like tons of resources and a very good community. Cons is, again, rigid data schema. Like if your application is growing, now you need to deal with unstructured data, like you cannot have SQL. You might end up implementing a NoSQL solution. And now your application has a SQL store and a NoSQL store, because SQL cannot deal with unstructured data. It's just not designed for it, right? So rigid data schema. Querying slows as data grows. If your table consists of like millions of records and like millions of columns, it's problematic. It will slow down your query. It will cost you more, and it is not easy to scale for such kind of data. Querying can become a bottleneck or can become a problem. And again, costs, right? Like maintaining these databases, like scaling, you need to have like database systems, like maintenance is like very expensive. Hard to scale, like I said, like you can only scale such a system vertically, right? You can do some kind of like horizontal scaling, but it will be like really hard to like do it, right? Like you'll come with all sorts of issues with partitioning, and you need to like figure out like how would you configure like your partitions and how complicated your application code needs to be if you're scaled horizontally. So it becomes complicated, and as your data grows, right? So it has its challenges. NoSQL is like basically like non-relational data. So data can be stored in all sorts of formats, JSON documents, key value pairs, column wide, graphs, which has node and edges, etc. There's a huge list. Data has no relationship. Data doesn't have to have any relationship between them, right? It can be like you're just storing images, right? Images don't need to have any relationship between them, so it's fine, right? So like, yeah, someone's profile information, right? There's just an image. You just attach it with some ID, but like you don't need to have any other relationship, right? So like it's very simple like that, very straightforward. You cannot join between data because there's no relationship. It's suitable for huge volumes of data, even like not only in scale, like millions of data, but it can also be like, okay, like I'm storing like YouTube videos or like really heavy images. So even if the volume or the size of the data is like huge, great. NoSQL is designed to address these things. Again, scale out architecture. A lot of NoSQL data structures are like distributed, so you can scale up and down. These are designed for that feature, so it's like really efficient. A lot of functionalities come out of the box, which makes our lives easier. You just keep adding more instances. Again, distributed, so no single point of failure, which is the biggest plus. Less hardware maintenance because a lot of these systems are virtual, and you have like app servers which take care of stuff. And even if you need to like add more hardware, it's like cheap, simple hardware will do your job. You don't need to buy like expensive systems which need to have very super great quality. Flexible of storing unstructured data, right? Like a data model is flexible. You can have 5 different kinds of data models, unstructured data, semi-structured data, all good. Can store massive amounts of data is typically used in the big data world, right? So like when you're storing petabytes of information, SQL is not your best friend. Like you want an NoSQL data store technology, which is designed for this kind of stuff to like persist your data. Very agile, great flexibility for adaptability and faster querying, right? Depending on your data type and the tool you're using. A lot of these NoSQL technologies are designed for faster querying and reducing costs. So, well, depends, cost depends, but like they're really designed for like faster querying, really efficient querying performance, and like really like great flexibility with your data and scaling. So all these features come out of the box. Cons would be like, you don't get any asset properties, right? Like it only supports eventual consistency of data. It comes to like speed of fetching the data and even how available the data is. This is where we have to think about like cap theorem, which is the next slide, and learning curve is stiff for new developers. Like it is in our generation, like people know about SQL for like decades. So there's good community support. People know about it. DML, DDLs, we learned in like college and stuff. So we already know stuff, but NoSQL, if you're working in a bank, you'll probably not have NoSQL data at all. It's all relational. You're only dealing with like MySQL data, and like you only have like Oracle database or Postgres database. You never have to understand what column-wide data store is and what Cassandra is. Probably the farthest you would go is some kind of caching and key value pair. So like that restricts your learning curve. So if you're not in a corporate environment where you're dealing with NoSQL data at scale, you will not even learn these technologies. And like not everyone also knows about it. So there's a learning curve there, and kind of there's a limitation there. Few things to keep in mind when you're thinking about like SQL data. You need to like understand like what asset properties are, because all SQL relational data complies with asset properties. You guys probably know, but I felt like it's important to revisit this concept. It's fundamental. And when you're doing system design, this is the things you're thinking about, like 100%. When you're dealing with system at scale, you are considering cap theorem, and you will determine what your system can provide, can do and cannot do. So this becomes it's foundational, but it becomes very important. Atomicity, right? Like all changes to the data and transactions are executed completely as a single operation. If that isn't possible, none of the changes are performed, right? So you either keep all the data intact or nothing is updated, right? So that is what SQL. Well, SQL data needs to be compliant to these concepts, but when you use modern, any actually SQL tools, these kind of features are built in. So, but you need to, as a developer who is designing data models, dealing with data in and out, you need to know these concepts, very foundational. Consistency is data must be valid and consistent at the start and the end of a transaction. So if you guys are familiar with like transactions, rollbacks, commits, these kind of stuff in relational data or in SQL, you know that if you're trying to make a data transaction, your data needs to be valid and consistent throughout that transaction. And there should be no there's no fault there. If there's a fault, then it should be rolled back because the data needs to be consistent. Isolation is multiple transactions can occur without stepping on each other. So you need to design your system, your data schema in a way that on the same table, multiple transactions can happen. On the same data, multiple transactions can happen, but it doesn't put your system in a faulty state, or it doesn't put your data in an invalidated state, right? Different transactions can happen asynchronously, and the data is still valid, it's still intact, it's still correctly updated. Right? So this is isolation. And durability. When a transaction is completed, its associated data is permanent, it cannot be changed. Once you made the data change, all your data is completely updated, then it persists. It doesn't go away, right? Yeah, like this change, update to your data will persist till another new update transaction happens. Till then, your data will be the same, right? It doesn't change because of something else that happened in the system, or synchronously or something else, there's no other way to change it. So you have to kind of make sure that your data is durable. This is all related to like SQL or relational databases. When it comes to NoSQL or non-relational database, ACID does not apply. The ACID is not something we can promise. These are not the features, or this is not the quality we can promise when it comes to NoSQL or non-relational data. But there are other things that other problems we have, or other things we need to think about. It's the different design considerations we have, and the different kind of quality or different kind of feature we can provide when it comes to non-relational data. So what we can do, this is where the cap theorem comes in. We can provide consistency, availability, and partition tolerance. Okay, so like we can provide consistency where, all of our clients see the same data at the same time. Your data can be distributed among different databases, different caches, different even geolocations. But when your clients are querying some data, they all see the same data, and they see the same data at the same time. So like you're providing consistency of data, even though your data is completely, or your application is completely distributed. Availability would be your system continues to operate even when there are node failures or device failures. So like, like I said, right? If your application is distributed, you have 3 instances that are often your applications that are web servers, which are making sure your system is up and running. If one node goes down or there's some kind of device failure, the 2 other systems will make sure, or servers will make sure your system is up and running, right? There will be load balancing and stuff like that, but they will make sure your system is up and running. So even if there is a device failure, node failure, instance failure, your system is still available to all the users all the time. Partition tolerance would be system continues to operate even with network failures. So, distributed systems, there's a lot of networking, right? These systems are connected over the internet, right? There can be network failures for some reason, right? Even with a network failure, let's say all the servers in the East Coast have failed for some reason, but the servers in the West Coast are not, they're up and running. Then there's some kind of partition tolerance or something in place that you have designed which makes sure that all your data is still persistent, it's still there, it's still available, and your users can see this information, right? Your system continues to operate, is reliable, right? It works as expected, even when there's a network failure, because many times network failures are out of our control, right? Device failures can be quickly addressed with like a shorter downtime, but network failures not always. So this is where your partition tolerance happens, right? In the event of a network failure on a distributed database, something to keep in mind, you only get either consistency or availability. You cannot get both, right? So the challenge with CAP theorem is you can only offer 2 things at a given time. Your system can only be consistent and available, or it can only be consistent and partition tolerant, or it can only be available and partition tolerant. You can never guarantee all these 3 things, not even eventually. So any system that is designed like this, at scale, is distributed, is dealing with NoSQL data, you can only provide 2 things to your customers. That's the only thing you can offer. And you have to determine what your applications and what your data you're dealing with, that you want to only provide A and P, right? Availability and partition tolerance. You don't care about consistency. Or you want to make sure it's very data heavy, so you need to provide like consistency and availability, but partition tolerance you will not guarantee, not even eventually. Please note that these things, because it's a distributed system, your data will be updated eventually. So all of these things you get eventually, but you can only offer any 2 of these 3. And when you're designing such a system, this is the trade-off. This is the choice you have to make, what you want to provide. And there are different, in the diagram, if you see, there are different systems, right? If you want to provide like availability and partition tolerance, DynamoDB will give you that, Cassandra will give you that, CouchDB will give you that. If you want to provide consistency and availability, like relational database will give you that. If you want to provide partition tolerance and consistency, systems like Bigtable, HBase, MongoDB, they have all these Redis, they have all these features inbuilt. So use these kind of technologies, structure data accordingly, so you can provide consistency and partition tolerance, but you will not get availability because that is not what you are providing or what this system is designed for. Data pipeline, this is, I think, the last concept. Because you're talking about data partitioning, big data, like designing for data so much. One important thing that I also wanted to talk about is data pipeline. A lot of these sophisticated systems have now built data pipelines, to support their application and to process their data even offline. And petabytes of data, big data, is all streamed and processed through data pipelines now. And what we do here is basically we collect raw data. So any raw data here is anything you collect from the users, right? You collect this raw data. It can be ingested from very different sources. It can be ingested directly from a browser or from a mobile app, from even a different database or even different external application that you have an integration with. So you collect this data, different kinds of data, raw data from different sources. You port them over to one data store, 1 or 2 data stores, actually. It can be a data lake. It can be a data warehouse. And you're putting all this data there for analysis, really. Of course, it's giving you the persistence, but the whole point of storing all this data is that you're getting all this different data from different sources. Now you have a lot of data. Now you can do analysis on this big data. You can do all sorts of complicated analysis on this huge data set, which is very different. And you can do it all in one place, in your one data lake, in your one data warehouse, right? In one data store. This is where data pipelines help you. So what you're trying to do is like your data processing occurs before all the storage happens, right? Through any data repository you choose. It's all isolated, it's all asynchronous, it can be offline behind the scenes happening, right? So you can completely schedule or time all this. Data ingestion can happen for structured and unstructured data, right? Any kind of data that's collected, any kind of raw data. There's a lot that happens, but some of the simple things that always happen is you're getting all sorts of data, you would filter it to pick the data that really matters, right? You don't want to handle everything that you're collecting from users. Let's say you're transforming it, right? So you can have one common structure if you want, and then normalize it, right? Like removing redundancies and just analyzing and stuff like that. This is a very common operations that you do on this data you're collecting, and this is what your data processing really is. And you're doing all this for like one major reason: persistence. You get it out of the box. You get to store like petabytes of like big data, so all good, but you're doing really for visualization, all this, you get this one data lake or one data warehouse where all sorts of data is there, everything is analyzed, and now you can just create all sorts of dashboards from this data, right? You can do reporting, you can basically enable all sorts of real-time notifications from this data. So this is what is the benefit. There are a lot of tools that can be like, okay, these tools are doing data processing. They have their pipelines. Like Informatica Power Center, this tool has been there for like, I don't know, 15 years now. It does ETL, like extract, transform, and loading. You have Snowflake, right? It's a data lake. You have Google's BigQuery, it's a warehouse. MS Azure, Kafka does real-time streaming of data, right? So these all tools are like your data pipeline tools, and they're just doing all sorts of data processing and analysis, right? In the example, if you see, it's very simple example, different sources, you extract all that raw data, just staging area where you're transforming it, then you're loading it to a warehouse, or it can be a data lake, right? Your data is transformed, analyzed, processed, you're persisting. And out of that, you just want to create some kind of visualization, right? Some kind of analysis. Now you want to see some structure. And based on your dashboards, you're reporting, you're going to make sense out of that data, right? So data pipelines, when you deal with like applications that scale, have more and more features, you're dealing with complicated data and data of all kinds, you want to kind of make sense out of what is going on. You want to understand your data and build more features or solve existing problems and make more money. So data lakes, data warehouses help you do all of that. Just like couple simple system design diagrams. This is again, this will help us transition to like the next session, which is on 16th, where we will talk about like system design interviews, like how to give them. We'll go through some questions. We'll just try to actually solve like some design questions that are commonly asked. And this is a very simple diagram you might do in an interview, or even like just to understand, right? Like we talked about so many different things. You can see here in this diagram, we're talking about like different web server, application servers. There are two application servers here, one for authentication, one for APIs. There can be external integration. You have a cache layer, you have a batch processing layer, which it might be doing streaming too. Your data warehouse, data transaction, right? Like it's like a very simple application, but there's so much that's going in. And when you're doing system design, you need to understand all these things, and you need to make all these decisions, what tool to pick, what technology to pick, right? Like what are your trade-offs? Are you giving consistency and availability, or are you giving consistency and partition tolerance? And if yes, why? Right? And what tool do you need to use? How to do integrations? All of that you need to understand. It's a simple diagram, but there's like so much going in and so much you need to know when you're doing like system design. This is another diagram. This is a little bit more sophisticated, where you have different clients, you have your CDN for caching, you have your load balancers. There's two CDNs, they're based on like different geographic locations, right? You have your queuing, you have your pub sub setup, you have your workers, you have your app servers, you have your authentication servers, different caching mechanisms, different caches, you have different instances of a database, and they're all sharded, right? One, like there's a slave, which is only takes care of like N to Z, let's say names from N to Z, or names starting with A to M and stuff like that, right? It's like very distributed system, replications happening. Some databases are only for reads, some databases are optimized only for writes. So like, it's like, again, this is not a complicated diagram, but like there's so much you need to know to even come up with this design. Like this is a very good example of like designing Airbnb or something like that. You might want to draw this diagram in a system design interview, right? Or even in your design doc that, hey, this is what I'm thinking. It's a perfectly good example. So we are at the end of the session. I'm sorry we went overboard. We have a few more sessions coming up. 16th is the last part 3, the last session in this series. We'll talk about system design interviews. On March 23rd, we have an introduction to GPT-3, and April 6th is again a session with me about SQL Queries 101. This presentation is available on our GitHub repo, Women Who Code Backend Study Group repo, and this is being recorded, so this will be available on our YouTube channel. And there are some more resources if you're interested in volunteering with us, getting to know more about Women Who Code. There are technical tracks, events. You can join our Slack workspace and join our backend study group. And you can also contact us. I know we went a little bit overboard, but now would be a good time for Q&A. I'm also going to go through our chat messages. Feel free to like also unmute and talk. I think Matt definitely helped answer many questions.
Sure, Prachi. V had one question.
Yeah.
When you were talking about various types of database design and how you can make different decisions on how to break up the data. She was wondering if there's any kind of software or analytics tools that you use for that. I was thinking about your experience in Datadog or something else.
Yeah. So like we talked about monitoring a little bit in the first session. Monitoring is of different kinds, right? Like, are you monitoring your system's health? Are you monitoring if your system server is up and running? Are you monitoring your APIs and their performance, right? Like monitoring is different kinds. Are you monitoring for any log messages or any errors? So what are you monitoring and why is it important and how frequently are you monitoring? So different tools, right? Like if you have Kubernetes or stuff like that, you have a Docker instance, Kubernetes will help you monitor that, your health checks, right? Actuators will help you check for your health of your application. If you want to look at like your application health when it comes to logs and all the activities, Splunk will do that for you. If you want to monitor your API performance, your service performance, Datadog will do that for you. So there are all sorts of tools out there which give all sorts of reporting and monitoring. It just depends on how valuable your monitoring is and what you're trying to do. So definitely a lot of tools out there that come into the monitoring, error detection, security side of things, for sure.
Prachi, Monique is asking, are there any situations where you might build an app that requires both vertical and horizontal scaling?
I can something a real life application doesn't come to my mind right now, but it can be I can come up with an example. Let's see, like let me think, like you have something like goodreads.com, right? It's a very simple website. You can go search for books, you can read the book summary, the name of the author, you can look at the reviews, right? Read the reviews and stuff like that. Now, when you have such a simple site, again, I'm assuming things here, so don't like take it too hard, but just an example. On such a site, there's a profile section where you can log in and you can see your profile, right? A lot of people are going on that site, again, assumption, to see the search for the books and understand, get more knowledge about the books, the reviews, the author, all of that. They're not necessarily going there to update their profiles all the time, because Goodreads doesn't really care about your profile information, is not doing much with that kind of data, right? So if you're designing Goodreads, you might have more resources dedicated to book searches, storing the information about book and making that information available. And you might have less resources or even one server really that is taking care of all the user profile information, right? So if this is the system you have where one feature, one part of your system is like barely used, it doesn't have any scaling needs pretty much like at all, or very minimal and only peak hours, then you can just have profile related information on one server, and during peak hours, if at all, you can just scale it up by adding more resources, right? And once that activity dies down, you just get rid of the resource and you're fine. You don't need to add 10 more servers because like few users are looking at their profiles, so stuff like that. So like your application can be very vast, but certain parts of your application or product or their features just don't scale. They'll never scale that much, right? So for that kind of a system or application stack, you just want to implement like a horizontal scaling where everything else is vertically scaled. You want to implement vertical scaling where everything else is horizontal scale and has more instances, more resources, more servers. Again, I assumed, but that would be one example where, certain part of the system just doesn't scale so much. So with vertical scaling, you're fine. So this is where you have like a hybrid structure, hybrid scaling. Did I answer your question? I hope I did. Matt did share like a feedback form. Do we have that feedback form?
Let me paste it in now.
I'm gonna stop sharing the screen so I can share a link to the slides on GitHub. Let me get to that. 1 second. 1 second, let me get to that. If you go to, if you go to, here is the chat. Yeah. If you go to like our GitHub page, there is under Women Who Code, like backend study group repo, there is a folder called Meetup Events. We have these folders based on the date, and it has all the presentations we have ever done, everything since the last 2 years. So, it's like a great resource. And it's date based. So today's presentation is March 8th. So you have that. Hopefully that helps.
Yeah, and I've also just shared in the chat a link to a Google Doc, which you can fill out. If you thought this presentation had value, I did. I thought it was great. Thank you so much, Prachi.
Thank you.
But if you like this presentation, if you want to give some feedback, positive feedback would be much appreciated. Click the link, smash the link, go fill out the survey, and let everybody know what you thought.
Yeah. And if you have any ideas, if you have any topics you want us to cover, the feedback form is a great place for that as well. If you don't have any more questions, thank you, Matt, for hosting our session today. And thank you everyone who joined us. This has been great. And hopefully we'll see you in the next session, which is next Thursday. And you can just RSVP for the session on Meetup. Thank you so much.